random arrow here, but okay, cool. So good morning, everyone. Thank you for coming. My name is Abby. I'll be speaking on joint work I've done with Vineet Kaur, Peter Behorst, and Mark. And this is on intrinsic non-locality and device-independent key agreement. So I will explain what all these words mean, and hopefully we'll be done before lunch. And so as we
You have to click on the PowerPoint slide.
right. So conference key agreement is the task of distributing a secret key among more than two parties. And so for now, in this talk, we will focus mostly on the three-party case, and all of our results extend very easily to the n-partite case. So the ideal secret key is uniformly random, agreed upon by all parties, and independent of the eavesdropper. Now, since we are implementing a cryptographic protocol, we assume that, or don't assume, yeah, we assume that the eavesdropper is restricted solely by quantum mechanics, and we want to give the eavesdropper as much power as possible so that our key, when we do extract it, is as secure as possible. And so the ideal tripartite key, like I said, is agreed upon by everyone. So L's are all the same and perfectly uniformly random. So that covers everything within the parentheses, and independent of the eavesdropper, which I have put in as the system sigma E. So E is the eavesdropper and R is the rate of conference key agreement. Now our intention here is to upper bound this rate, and as we go on, I will explain more. And so now the conditions we have imposed upon ourselves come from this concept of device independence. Now, this is where we assume as little as possible about the instruments and states we have. So let's say Alice, Bob, and Charlie, as would be customary in these situations, share a state obtained from a possibly unknown quantity. I realize the word state is missing, but all right. Each party has access to a black box, which they can give a classical input to. So you can assume that Alice, Bob, and Charlie have their own little box, which has some share of a tripartite state, and they can click a button. That's their input classically, and we want to assume as little about both as possible. And so whenever they press the button, give it a classical input, the box implements a POVM, or basically a measurement, and the box displays an output, or a bulb lights up. So it's all classical, and we repeat this several times, and the outputs we obtain will be according to this correlation, where pi xa is the so pi x is the POVM implemented upon the input x, and a is the output that is obtained, and similarly for Bob and Charlie. And this is the correlation. Now we want to see how we can extract key from this correlation and then put a cap. And so this is general protocol for the tripartite state. We'll explain this part by part. And so first, let's focus on this. So what happens is Alice, Bob, and Charlie are given again a tripartite state. Now they have some shared randomness. So so there's like a coin in the sky, and whenever the coin in the sky is 0, they give these inputs. So X, Y, and Z are 0, 2, and 1. So Alice and Charlie can have their inputs can be 0 or 1, and Bob has 3 inputs, 0, 1, and 2. So when T is 0, I will call T equal to 0 key generation round. They input this very specific combination, and when T equal to 1, I call this the testing rounds. Alice chooses randomly from her choices of input. Bob does the same, and Charlie as well, no choice, has just one choice, and they all record the outputs that are obtained. and they repeat this n times, well, as many times as they want. And so now on to this last part. Now, no, the latter part. So LOPC stands for local operations with public communication. Local operations will self-explanatory. Public communication is, say, a print in a newspaper or people yelling really loudly, or a public talk like I'm giving now. And so Alice, Bob, and Charlie announce all their input states and a portion of their output states. And now you can obtain a lot of correlations any which way. They can be classical, they could be quantum. Some of them are useful, some of them are not. And so for key generation, we want to assert that the correlation we have is useful. And to do this, we need a test. Now, given that the test, that the correlation we have passes this test, then we can use, well, LOPC to obtain the final key state. Now, so in general, in all of our above analysis, the key resource is this correlation. So we want to test, we want to be able to tell whether this is useful, and then bound how much key we can obtain from it. And in all this, our enemy is the eavesdropper. So given that Alice, Bob, and Charlie can't communicate when they're interacting with their, can't and shouldn't communicate when they're interacting with their black boxes, because again, classical public communication can be intercepted by the eavesdropper, and simply write it down and the eavesdropper will have it. So at random, they choose their inputs X, Y, and Z, and W is a winning function, which is 0 when they win, which is 1 when they win, and 0 when they don't. And this is the winning, this is the condition for winning. The more anyone who's dealt with such a scenario before will notice that if I ignore the C in there, this is exactly the CHHS, the general the normal bipartite CHHS game that we're all used to. And this is the tripartite or a tripartite or n-partite extension. And so if the winning probability is less than or equal to 3 by 4, where we can say for sure that the correlation we have is local, is of this form. And again, since lambda is classical, we assume the eavesdropper already has it, and hence this correlation is well, useless to us, and we can't obtain any secure key from it. But if the winning probability is cos square pi or 8 or 0.85, we can assert that the underlying state shared by Alice, Bob, and Charlie is a GHZ state, and GHZ state is this is the GHZ state, and so this is what we want. And so this is how we test whether our correlation is useful. Now in all this, what can our eavesdropper do? The eavesdropper can have, so the eavesdropper can have an extension to our correlation given like this. The more, so if this is kept, so this is just a classical register. This is the real quantum bit. These are the measurements that were obtained, and this is the shared state. So Alice, so the eavesdropper is part of a larger quantum system that has access to a quantum system that is, that they're entirely part of a larger one, and a small part of it is what Alice, Bob, and Charlie have access to. And so a more informative form is this. So this here is our correlation, and with every such setting of correlation, Eve has this thing, has a quantum state, which she can use to, well, eavesdrop. And so now if our state, like I said, were a GHZ state, then, and so basically if our correlation passes this test, then we can be sure that this came from a GHZ state, and that, and whatever this is completely independent of the rest of this. So that is why our CHHS test, parity CHHS test, as it's called, is a very useful test, and, well, assures us of a lot. And so this is our, finally, this is our ideal key. And so we expect that, so LA, LB, LC are the actual key. This is whatever information the eavesdropper has. These are all the input settings that were published, and this is all classical communication or public communication between Alice, Bob, and Charlie. And so we want our key that's again agreed upon, uniformly random, and independent of anything and everything the eavesdropper may possess. And so the rate is again R, and we want to upper bound the maximum rate. So we want to upper bound an upper bound, and which we call the capacity. So that. And so now we need to pick some quantity to measure this. We want a quantifier, and we choose. That's not from us, right? Okay, that's not cool. And so what we want is a good measure, and what we've gone with from prior experience is at least our initial guess was conditional total correlation, which is given by this. I understand this may not make sense to anyone looking at it for the first time. I will tell you that it is an M-partite generalization of quantum conditional mutual information given like this, which I'm sure a lot more of us are familiar with. And so now why we've chosen this is because if there is a short Markov chain, basically if there's this Alice and Bob, and they were correlated solely by Eve, through Eve. So all correlations were provided by the eavesdropper, then well, you have no secure key, because every bit of key you obtain. So if the eavesdropper is the only way, is the middleman between Alice and Bob's correlations, then whatever secret key they obtain isn't really a secret. And so similarly with Charlie, even with Charlie around, if this were the case, they wouldn't obtain any secret key. So what we want to do is somehow pick a quantity that goes to 0 under these conditions, and so the one we picked is conditional mutual information, which generalizes total correlation, which generalizes conditional mutual information. And yeah, as soon as my slides so we want a quantity that goes to 0. Basically, we want something that acts similar to conditional mutual information, and so we picked we picked conditional total correlation. And so now how do you upper bound? Now you have a quantity that measures that we hope measures the amount of secret key, right? And now how do we actually do it now? So any extension system, that is the system E that we saw, and any operations that the eavesdropper can do, basically our eavesdropper can do anything as long as it's within quantum mechanics. And so we call that an attack. And so if we want a reliable upper bound, if this is our actual key rate, if it's way up here, this is a completely useless upper bound. So we want to bring this upper bound as close as possible to this, so we minimize over all attacks, so to bring it here. And we also don't want it to undershoot and go all the way down, and so we maximize over all ways of choosing input pairs, and so it becomes a fun min-max quantity, which we will promptly then upper bound again. So this is our quantity. So you can see it is an infimum over all infimum over all attacks, and a supremum over all ways we can choose our X, Y, and Z. And so this we say is an upper bound, and we also show that it is indeed an upper bound. And now we want to know how it compares to a lower bound. The yellow line is the lower bound, and the blue line is nice, neat, and clearly an upper bound. And so the underlying state we picked for this is the GHZ state, where each of these qubits is sent through a depolarizing channel with the probability of depolarization is p-type. And so we've plotted it against that. And clearly, if there wasn't a deportization channel, we'd be all good and we'd get perfect key every time. And now there are obviously, now since this is of course fairly complicated quantity to begin with, so we'd like some useful properties for this quantity to hope to calculate it, and these are a few. Plus, sorry, that star should be a plus, not a into. So if they're product, we should just be able to add the two key rates together, and we want it to be, so that's called additivity. We also want convexity, because if we probabilistically mix two correlations we could obtain, we want we want it to nicely break down into these. And we also have local, we also want to see, so a thing that we take for free is local operations and common randomness. So the common randomness, like I said, is again a coin in the sky that flips whenever it feels like. And so even if we can see that, and since the eavesdropper can also see that, we do not want our quantity to increase under such a resource. And so we also are able to show that it indeed, the upper bound indeed does not increase. And so now we want to generalize this to multipartite situation. So I will only discuss tripartite so far. We want to generalize this to a multipartite situation. So useful chain, we'd like a sort of, we show a useful chain rule. So A11, so the first index is associated with the party. So A11 is the first trial of Alice, A12 is the second trial of Alice, and so on and so forth. So we'd like to break it down into two nice terms, but unfortunately we're also stuck with these terms. And so with, as long as these correlations are obtained from quantum, well, as long as they are quantum correlations, we can put those terms to 0. And so using these, we can show that we can show that this quantity, which is again a min-max, but again, since it was conditional total correlation, I can like expand it to fit how many ever, and all the above properties work just fine. And again, it is an upper bound, it's additive, convex, and monotone under local operations and common randomness. And so so we sent the paper to a journal, and yeah. Huh?
Why do we want an upper bound?
Why do we want an upper bound?
Yeah.
So what the part of why we want an upper bound is that if, of course, we have a lower bound, so we're hoping that we can, bring the upper bound as close as possible, bring the lower bound up as possible, and we'll have an exact rate throughout. That is part of our strategy. And so there are lower bounds. There is a case to be made that we need better lower bounds and upper bounds. And so our aim is to bridge this gap to bring it, say, as close as possible to these. And so this is the ceiling. We want the floor and ceiling to make as small a room as possible. That is our aim. And yeah, this is one step in that direction. And the first one's the archive version of this paper. The others are useful resource citations within the presentation. Thank you for listening in.
I actually had a question. We go to question 7.
Please. Remember where that is.
Sorry, you go to 6. Right. So you define this extension as basically anything that the eavesdropper has.
Yeah.
The overall system, right?
Yeah, basically like this.
Right. Is there any reason we want a mixed state? Why not a pure state? Because the best case, the best eavesdropper would have a pure state extension, right?
Yeah. This could be a pure state.
This could be a, I mean.
Also,
first-
we do not know for sure if that is actually the case. If that is well and truly.
I understand this situation, but since you have an infimum later.
Again, that
infimum
infimum,
of a pure state be enough?
that is,
Yeah, and that's the point.
that's the problem.
You have tighter bounds with these.
With mixed states. So, yeah, the, okay, so the small caveat that I might have glossed over is that that infimum is intractable. So so our aim is, so when I said that there is a lot of work left to bridge this gap, it's mostly with the upper bound because that infimum is quite difficult to do. So people have found clever ways to like bring it lower and lower. And it has, a lot of them have been mixed state strategies. So again, if it were a pure state, the eavesdropper would have a lot of quantum side information, which we as eavesdroppers don't really know what to do. So it's nicer if it's a bit classical, and then the infimum becomes easier to track.
So we don't know how to place a bound in the dimension of the eavesdropper system. It could be unbounded. This quantity could keep getting smaller and smaller. We actually, maybe said it's intractable. We actually suspect that it's intractable. Like
Yeah,
it might
suspect.
be very uncomputable.
Yeah.
To evaluate this quantity.
So what they usually do with lower bounds is there's something called an NPA hierarchy, which you can, wait, not sure. So here I've taken product structure between the eavesdropper, between the POVMs. I can replace this with all of them just commuting, and then I can find, then I can do the, well, I can do the lower bound for the lower bound. I can do the infimum for the lower bound, but that's an SDP, and this quantity as yet does not render itself very nicely to an SDP.
Mark, you were saying that the infimum, like, as you increase the size of the eavesdropper system, it reduces. That's a
Yeah.
good thing, right?
Yeah, you get better bound.
Okay. You're saying
But
like.
then, to evaluate it for higher and higher dimensions.
Yeah.
Yeah, so we make like guesses as to what would be good.
Good.
attacks.
Yeah.
Eavesdropper to try.
Is there like, how big have you gone with the eavesdropper system?
I've
Not very
equaled,
big, right?
not very big. I've equaled the size. I've equaled the size of the system itself.
Right.
I mean, of the AVC, so the eavesdropper has a similarly sized system. That's as big as I've gone. But yeah.
Any other questions? All right, thank you. And thank you to all the speakers. Lunch